Hello and welcome back, and apologies to the conversations I just cut off, including my own. We are now going to take a slightly different approach and get into some more of the technical aspects that go on behind the building of the models, and also into where some people might be thinking about going in terms of all the wonderful things out there in the new digital management world. So I'm now going to invite Michael Finger from the Victorian Department of Environment, Land, Water and Planning. And Michael is going to share the Victorian approach to collective next generation model management to meet industry needs. Welcome, Michael.
Thanks, Trudy.
We can hear you. I think we're right to go.
I'll jump on my screen. Okay, can we see that?
All good.
Okay, so yeah, my presentation is about the Victorian approach to collective next generation model management to meet industry needs. It's a bit of a mouthful, but basically Dept is a custodian of a number of hydrological models, and it also has a coordinating role across the water industry in Victoria. So we've got this role to sort of manage models. And this presentation is a bit of an update on some of the issues we've been exploring and the way that we're thinking to possibly go. And that's what I'm going to share today. So I'll give a bit of an overview of how hydrological models are used, some of their characteristics, and what this means for model management. I'll talk about our historic sort of approach to model management and some of these possible new approaches that we're exploring, some of the issues to overcome, and what we've been doing in this space. So this is probably a familiar figure at an eWater software conference, but we'll use it just to flesh out what some of these models are used for. If we take a tour around from about 1 o'clock, we've got the ecological assets, so rivers, wetlands, estuaries, supporting environmental values, significant volumes of water. I think it's around 650 gigalitres for the Victorian environmental water holder and nearly 800 gigalitres for the Commonwealth in Victoria, and a whole lot of other environmental water tied up in other arrangements. And, you know, models were instrumental in sort of securing that water, and they're important to get the most out of that water and demonstrate the value.
Sorry to interrupt, Michael. We can see your notes, which doesn't bother me, but if you don't want us to see them, you might want to hide them.
That's weird. Yeah, okay, hang on.
Slideshow to correct output monitor is one suggestion. Present mode, maybe?
What can you see now?
Looks okay at the moment. We'll see how we go.
Okay, is that just the initial slide?
Yeah.
Okay.
Let's try and hit present and see what happens.
Yeah. Let me try and change the screen. Okay, I think that should be better now. Let me know if you can still see the notes, because it'd be better if you could see the whole slides.
It's perfect now.
Okay, great. Yeah, so cities and towns, so we've got, you know, millions of people and businesses, water and wastewater services, and billions of dollars in assets to support water security for those people. Models are used to inform that. Irrigation, it's one of our, you know, it is the largest user of water. You know, thousands of gigalitres and billions of dollars just in the value of that water in the market. and it's critical to food security. There's all the dams and weirs that are instrumental to support that. There's a huge historical investment in those, and they need to also adapt to new challenges to operate efficiently, delivering these large volumes of environmental water and being part of a growing system that has alternative water sources such as desal and stormwater, recycled water. And then there's climate and land use, which it's risks to water security and water quality. So we've got these different model applications, and it's not just one person, one organisation that's interested in those. For example, in Victoria, we've got 10 catchment management authorities, 19 water corporations, the Victorian Environmental Water Holder, Commonwealth Environmental Water Holder. There's Dept has an overarching role, and there's others, and then there's consultants that are also supporting these different organisations. So models are used to support, these very important decisions around infrastructure and planning and operation. There's a big range of these applications, and we've got a lot of different model users. We'll step away from that figure and look at a real model here. This is the Golden Broken Campaspe Coliban Loddon interconnected system. This is the level of complexity that's needed to represent the water sharing arrangements in Northern Victoria. By the numbers, you can see here there's hundreds of nodes and links, functions, model variables, multiple ownership systems and resource assessment systems. So these models are complex. And this model in particular has been developed over a number of years. It's been sort of developed in parallel to source, building up over the time. And it also depends on knowledge developed over more than 30 years with the predecessor sort of models. So models are complex, they're long-lived, and there's a significant investment of time and resources in the models themselves. Bit of a recap. So models support important decisions. So they need to be robust, transparent, and defensible. They are used for a wide range of applications, and they need to be fit for purpose to those applications. There's a large number of model users, so it needs to be available to those users. And there's a significant investment in time and resources, so you need to manage that investment over time. And some of the outcomes we're looking for with our model management approach is that the models are secure and available, they're auditable, we've got consistency across models and applications and good practice, that the models are accessible, we minimize duplication of effort and share information and build capability across the industry so that we can get value for money. And we also want to be able to measure that value so we can sort of justify this large investment in modelling. Now I'll talk about some of the possible approaches to manage models to meet modelling needs. The first one's sort of the business as usual. Each organisation or each application has a model or version of the model that they need for that purpose, and you sort of share information across those models as required. So the good things about this approach is that each model is configured to meet the needs of that organisation or application, so it's fit for purpose. And you don't have any overhead by including things in the model that are not really relevant to you. Also, you've got your one model that you look after, so you don't have to worry about accessing any models. Some of the problems are there's a bit of duplication of effort. Sort of that sharing of knowledge across models is a bit of a manual process. Read through the last 3 or 5 reports to figure out what's going on over time. And you also miss opportunity because you might miss out on some work that's happening in parallel. And you can end up with a lack of consistency where, a part of the model that really should be the same ends up being different. And that ends up with an issue where you don't have a single point of truth. Some of the possible different approaches would be a single model. So everyone agrees to work on one model. You sort of guaranteed consistency in that way, and there's no duplication because everyone's working on that model. To make it work, you'd need robust access and maintenance agreements. And some of the problems with it really are that there's a big overhead. So if the model has to have every location and everything that everyone's interested in, it becomes a really large model, and you need to maintain all those things even if people aren't using them all the time. Similarly, the runtime, as you add all these things in, will get really large. And there's a risk that the model's not maintained. So if someone needs to quickly do some work on their little area of the model, they don't want to spend all the time and effort to update the whole model, so they'll just do their bit, and you'll end up with another version of the model, and really the single model disintegrates. A better alternative might be linked models. So that's a separate model for each spatial area. Maybe that's a basin scale or smaller scales. So you don't have that duplication in a spatial sense. So you don't have that overhead in running a big model when you don't want to. Similarly, you still have the issue of needing to be able to access those models. If you need to link up two models to do your work, then you want to have a good agreement in place that you'll be able to access and have an up-to-date model. And while the spatial in a spatial sense, there's no overhead, you still need to have all the features. So if you want to look at farm dams, you need to have farm dams in all the models, and other people might not be interested in that. You might need to customize the models anyway, so there still sort of has to be different versions. And in some ways you sort of have similar risk to the single model. It's not as bad, but there's still this issue of you always need different versions of models that are fit for purpose. So the last option we're looking at is this separate models with shared elements. So if you can think about a model, it's actually like a collection of building blocks, different model assumptions, inputs, parameters that go together to build up that model. And while you might have two different models, many of those assumptions and sort of elements will be shared. So the idea would be to have a sort of fit for purpose model structures and a systematic way of sharing those assumptions across models. And if it's systematic, there'd be a reduced that duplication of effort in terms of reviewing models and finding where they've changed and updating them. It can achieve the consistency where it's required, but also the flexibility where it's required. So you can have fit for purpose models, and you have a minimal overhead because the models are fit for purpose, not over sort of designed. Of course, you still need these access agreements and making sure it's up to date. And there will be extra work in configuring the shared aspects of models, and there'll be a bit of a learning curve to this new approach. Common thread is to move away from the business as usual. You need sort of these technical solutions to allow multiple users to access, configure, and run the models. And you need some governance arrangements to support working in this new way. As a bit of a recap, I think the single model is probably not really feasible. You'll never have one model that's fit for purpose for all applications and scales. Linked models may be suitable for some applications. And we're looking to explore this idea of the separate model with shared elements further, because it seems like it might be a good approach. Possibly there'd be sort of hybrids of this approach and linked models. So to give you an example of what that looks like, have a look at one of our catchments in Victoria. This is the Barwon Moorabool catchment. It's actually two catchments, but they're sort of managed collectively because of the way the two major towns, Ballarat in the north and Geelong, are supplied share those sort of catchments. In the north, Central Highlands Water have a source model that covers their area of interest, the catchments and infrastructure up there. Similarly, in the south, Barwon Water have a model that covers their areas of interest. And Dept has a sort of an interest to pretty much the whole catchment for things like farm dams, environmental flows, and understanding the water sharing arrangements in the whole basins. So in terms of model management, at the moment we've got these two models: Central Highlands Ballarat source model and Barwon Geelong source model. Dept currently has a realm model, and we're wanting to build a source model to meet our departmental needs. But there's no good us just coming along and building another copy, because that would be a duplication of effort. So one option might be that we build our model, and when we do the initial build of that model, we reconfigure the shared elements so that they can be sort of shared across the models in a systematic way. And then once you've got this set up, down the track, if Central Highlands Water do an update to their inputs, you could pull across the relevant inputs into the models that need them, into the Dept model or the Barwon model. Another example would be that there's a project to look at, I don't know, new water sharing arrangements, a lot of consultation and scenario modeling, and then everyone agrees that scenario B is the right one. You can then take that from the model and merge it back into the other models that need that. And the third example would be Ballarat is connected to the Northern Victorian system through the Goldfield Super Pipe. So you could take our GBCCL source model and get the seasonal determination and use that as an input to the Ballarat model and the Dept model. Some of the technical aspects to overcome with this model management, we need the models to be auditable, so version control figures in. They need to be secure and accessible, so probably cloud is the solution. We want consistency and good practice, so that's things like the practice notes, the MDBA practice notes, and probably some more specific things around the individual models. And we want to minimize duplication and maximize value, so we need systematic workflows. Some of the eWater source functionality that will support this approach would be the data source reload on run, scenario input sets, and the scenario compare tool. And then also possibly some other tools that sit around source. In terms of governance, you need an agreement to work in a new way. Some of the issues would be what are the responsibilities of each organisation, minimum standards to adopt for modelling and documentation, this process to identify which models and which model elements should be shared. There's the access to models. I mean, it's one thing to get a cloud sort of service and put the models there, but what should the models be used for? There might be a need for confidentiality. The issue of implied endorsement of modelling outcomes. If someone uses or misuses a model and then it was your model that they used, so they might imply that you sort of agree with that result. And then also intellectual property. So is it bundled across all the models, or is it stay with the model? Does each model element, does that have an owner in terms of the intellectual property? And Victoria, we're engaging with stakeholders via the Victorian Hydrological Modelling Group. We've been discussing some of these things like IP and model sharing. We've developed business requirements for a model management system with targeted stakeholder consultation. We're evaluating existing solutions, and that includes eWater's model provenance tools. It's pretty clear that definitely there's a lot of synergy with those tools and what we're wanting to implement. And we're just working out, how could we adapt or complement those with other things to meet all our needs. And we're also discussing these different approaches, the single model, linked model, or shared elements approach with stakeholders in Barn, Warrable and Werribee basins. So yeah, I'd like to thank Victorian Hydrological Modelling Group members that have supported Dept, in particular Melbourne Water, Central Highlands Water, Barwon Water and Western Water, who are discussing this sort of pilot approach to model management. If you've got any queries beyond the question time, you can email me. So yeah, thanks.
Thank you, Michael. So I'll just let people think about their questions. Model management is something a little bit tricky for my mind, but having been responsible for trying to understand how decisions have been made long ago in the past, and justifying them, then I think it's absolutely something all modelers should be doing. So good luck with that. No technical questions out there? Do you foresee that it could be, I don't know, everyone's got their own opinion about their models, and there's a tradition of keeping them to themselves and hiding away. What sort of cultural barriers do you think you might be up against?
Yeah, I mean, I think that's when I was talking about the governance arrangements, like those are some pretty thorny issues around, particularly like someone using a model and implying that you sort of endorse their modelling result.
Yep.
It's because they used your model to do it. You can make a model say anything if you press the right buttons. So yeah, there would have to be in that agreement, like probably limits, maybe some right to review or something.
Sure.
Yeah,
Yeah.
exactly. But that'll be probably the most difficult part rather than the technical side.
Well, good luck. And definitely the advantages of overcoming some of that historic duplication and going off and building something when perhaps there was already something out there.
Yeah,
all right then. Well, stay tuned for model management, because I think Jeff Davis will talk about some of our eWater's advances in that in his session too. Well, thank you, Michael. And we will grab Michael in the networking sessions if you've got some questions. All right. I'm now going to invite Aaron Trim from New South Wales Department of Planning, Industry and Environment, I hope. Aaron's going to share some work that he's done doing automation through Python, workflows for consistency and efficiency in modelling. You might have noted yesterday that Dishmanta and Rachel both, when they were speaking about the hydroclimatic modelling, that they both mentioned Aaron's work. So see if you can remember those linkages. All right, thanks, Aaron. We can see your screen.
Working? All right, great.
You look right to go.
Great. All right. So yeah, I'm here to talk about automation through Python workflows for consistency and efficiency in modeling. And I'll just note that I'm a water resources modeler at the Department of Planning, Industry and Environment, as noted. So yeah, as Trudy explained, yesterday my colleagues Dishmanta Dutta and Rachel Blakers talked about how we use stochastic modeling to inform regional water strategies decisions. So if you have any questions about that, hopefully you asked them yesterday. But in short, what we have are these existing river system models that were calibrated to the observed data. And now we've taken this and put stochastically generated climate data with these. And so what this does is it gives us, in theory, equally likely climate simulated for over 10,000 years, which we can then put through the model and estimate what the effects of that varying climate has on the river system. And then on top of that, we've also used the same technique and applied some sort of climate projection, whether that be NARCLIM or a change in East Coast low event frequency. It doesn't matter. We've applied that to the same sort of stochastic data set. And for the purposes of this example, we're going to be using NARCLIM scaling. This on the right, the tree on the right is how we evaluate the model options for regional water strategies, but we're going to be focusing on looking at the base case just for simplicity in this presentation. But just note that the process is more or less the same. You've just got 1,000 replicates of 40 years rather than a single 10,000 year sequence. So the first problem we come across when we're looking at this data is that the data size. We've got 10,000 years of daily data, and that's every input and every output, which is 3.6 million rows that Excel will absolutely refuse to open. And even if it did open it, it would be terribly slow at processing anything. That equates to roughly 75 megabytes in a CSV format, and that's going to be for every inflow location you have, every evaporation station you have, every rainfall station you have, and importantly, every single recorder that you put on in source will be roughly 75 megabytes. So this means your source results are going to balloon out. They're going to be at least 1 gigabyte for a small system with just a few nodes that you want to look at, and is easily going to reach up to 100 gigabytes if you have a larger system and you're trying to look at everything of importance. You want to look at all the gauge locations. You want to look at all the diversions. You want to look at all the inflows. So this becomes a big problem. And then on top of that, as we looked at the previous slide, we have at least 2 of these 10,000 year sequences and possibly more for the options modeling. You get your base case, your climate change and options. So yeah, you've got 100 gigabytes here, 100 gigabytes here, 100 gigabytes here. It ends up being a lot of data. Now, how do we process that? The second problem we have is the length of results, so we can't treat this time series like modelers may have done in the past with their instrumental data sets. As you can see, hopefully in the bottom left figure, that is a storage volume time series, a daily time series over instrumental period, and then the same storage in the stochastic modeling. Now, in this instrumental period in the bottom left, you can kind of do an eye test and see how the storage behaves. But once you move it to the stochastic, you've got absolutely no idea what's going on with an eye test. And so things like what was the highest level in the dam, what was the lowest level in the dam, what's the longest, shortest, and even what are individual drawdown events sort of lack meaning by themselves. So we needed then to look at a method of just determining the variability of the storage volume rather than looking at what is the lowest level in the storage, for example. And the last problem we come at, well, not the last problem, but one of the other problems we come across is how do we run stochastic models in eWater source? Because source wasn't exactly designed initially to run such large time series. And also, how do we sort through the results so we're most optimal with our use of the recorders, given that each recorder is 75 megabytes on your hard drive and in your RAM? So the way we've come up with initially in that bottom left is the standard folder structure we have for setting up the functions in order for you to be able to run your stochastic model. You'll set up your recorder set to just record this function folder, and you'll run it as is with no other recorders. And then within these folders, the modeler can set up functions to represent, in this example, f_gs would be the annual water determination for general security, and probably just links straight to a modeled variable. But this use of functions allows the modeler to customize this. For example, in some river systems, the relevant storage information is the sum of two storages. So what the modeler can just have is a function that adds those two storages together. And that saves a lot of work in how we process the data because it's all done upfront by the modeler. They tell us what's interesting, what they care about, and we can just process this function folder results. The second thing we do is we replace the data sources in with input sets when we run the model for stochastic or instrumental or stochastically scaled NARCLIM scale stochastic data set. So we have all the input data set to reload on run, and then the input set, we do this step here and we replace the file name. And that does a few things. The first thing it does is it makes it easy to have multiple climate scenarios. You don't have to have multiple inputs in the source model itself. And the second thing it does is it saves you having to save either multiple large project files with instrumental and stochastic and NARCLIM, where they're all the same except the inputs, or save them as one really, really big RS project file with all of the input data in it. It just sort of approximates input streaming, which I'm aware that eWater has been working on, but we've been doing this for about a year now. So this is what we've had to do in the meantime. So now we've got that, and we save the entire run to a .res.csv format, which is not particularly space efficient, but the netcdf file, as of now, only supports up to 4 gigabytes in size in eWater source, so we can't use that for these big model runs. Okay, so that's how we can run it. What do we actually want to get out of this? So we worked with our planning team who's working on the regional water strategies, and we got them to ask us all of the questions that they'd want answered from the stochastic runs. And here's a small subset of these, and we'll just sort of explain how we answer some of these questions. What are the annual inflows to the major storages? What are the seasonal trends in streamflows? Could droughts be the same or worse than what we've experienced in the past? What is the reliability of supply for regulated water licenses? So we'll just go through some examples. Oh, sorry. And we developed the DeepI stochastic modeling workflow in order to answer these questions, which is a Python application. And what it takes as input is all of those source.res.csv files that you've saved because you've run your stochastic and your climate change scenario, for example. And then a JSON settings file is used in order to let the modeler customize what they want. In that picture, you can see there, that is the part of the settings that defines which metrics they actually want to see. But you can also customize other things like important thresholds in storages that you want identified and things like that. And then it produces a standard set of metrics for your storages, flooding, annual water determinations, diversions, supply shortfalls, flows, and inflow sequences to storages. And then it takes all those standard figures and it plots every res.csv that you've supplied the program with on the same plot so we can get a comparison. So we'll go through some examples now. So this is an example of storage inflow metrics. In the bottom left, we're seeing an exceedance probability of 24-month inflows to Split Rock Dam. And so the way you can kind of read this is at each point on the graph, you have that percentage chance of getting at least that amount of flow into the dam over any given 24-month period. So for example, on this plot, the 20 percentile, there's a 20% chance of getting at least 200,000 megalitres into Split Rock Dam in the instrumental period, a bit less in the stochastic, and about half that in the climate change scenario of run. So this will let the planners decide on what kind of risk factor they'd like to associate with their storage inflows, rather than just say taking the the minimum inflow sequence that was observed previously. That answers question 1. What are the annual inflows to the major storages? In the bottom right plot, we see the monthly flow into Split Rock Dam. The line is the mean, and the shaded area is the 95% confidence interval for the 2 stochastic runs. And the instrumental is simply the mean. And this shows the seasonal trends, answering question 2. What are the seasonal trends in streamflows? We can see that in the present climate, we rely a lot on inflows in the winter, but the stochastic NARCLIM model implies that perhaps those winter flows might be significantly reduced. Here's some example metrics for river diversions. This plot shows the average annual diversion for a given license type over 130 years. For the instrumental period, this is itself, but for the stochastic period, this is the worst 130-year period that can be sampled from the stochastic data. So in this way, we're sort of saying what is the worst alternative instrumental period that we could have seen, and what would its average diversions be? So you can see for the general security, this approximately halves in simply the stochastic, and then halves again in the NARCLIM scenario. And again, this answers question 3. One of the ways of answering question 3, could droughts be the same or worse than we've experienced in the past? And now for the Awd metrics. So we've got a similar quantile plot to what was seen before for the inflows to the storages. We've got exceedance probability of a given Awd announcement on a given date. In the bottom left, the 30th of June, and in the bottom right, the 1st of July. Or 2nd of July because of time stepping. And this is able to be set up by the modeler. They can pick which dates are of note to their model. In NAMOI, this is continuous accounting, and these were the 2 most important dates, but an annual accounting might only care about the 1st of July and no other date. But as we can read off again, at the 20 percentile, there's roughly a 200% Awd in the stochastic and the instrumental, but only 125% in the NARCLIM scenario. And this answers one of the ways of answering the question, what is the reliability of supply for regulated water licenses? Okay, and then on top of those standard metrics, we have what we've called environmental flow metrics. So when we work with our environmental science team, they are mainly concerned with certain flush events or cease to flow events at points in rivers for flow. And so this varies from valley to valley, location, gauge to gauge. So what we've needed to put into this is some way of customizing this. So that settings far down the bottom, it's probably a bit difficult to read because I haven't put any comments in, but that is the customization where the modeler can decide at a given flow output location, what we're looking at, number of events of days above a threshold, or events of a certain length above threshold or at a certain time of year, or for a certain number of days, and the median length and a few other things. So this set of settings down the bottom produces the table up here. Okay, and so what challenges do we have in developing this? The first was eWater source date limitations. eWater source can't quite do 10,000 years of run because of its date library, but it gets kind of close enough for 10,000 years. However, when we start running some other models that have 100 repetitions of 130 years or 13,000 years, we've had to run 2 separate models with a large overlap period so that they converge and then join those results together to get this to work. Similarly, in Python, we had a lot of trouble with the same problem. The inbuilt Python library for datetime doesn't support 5-digit dates. So we had to write our own little library in Python in order to do all of the little date operations that we needed to do, aggregating to monthly and yearly and water yearly, etc. The other problem we have is computer memory limitations, because as we said, we've got 100 gigabytes, 100 gigabytes, 100 gigabytes. You've got to load that all into memory, which is going to be in the same sort of order of 100 gigabytes in the memory of your computer. We haven't really overcome that issue. We just have bought computers with more RAM to run these workflows on. And that's sort of the same answer to computational efficiency. We are using the NumPy and SciPy libraries in Python, which, if you don't know what they do, they sort of just pass the information to a dumber but faster program, do the calculations, then pass them back to your Python script. Okay, and some wish list or things we'd like to improve on. Again, the memory efficiency, what we can do is take the results, chunk them up into, say, 10 gigabyte chunks, process the statistics in an aggregate form on each of those, then combine the results to get the end, which is something we may do in the future when we get to some really big models that even our server computers can't handle. Computational efficiency, always looking for efficiency gains in computational efficiency. That's just a tinkering and ongoing process. But the main thing we'd like to improve on is to get extra flexibility and user accessibility to that program. I'm sure when you guys saw those little snippets of the JSON file, you had no idea what they meant, and neither do a lot of the users who haven't seen this before, because it's hard to communicate what needs to be put in each location, which ones they actually need to change and things like that. So getting some sort of GUI front end chucked onto this that aids the user in putting in all of the information that they need would be fantastic. And while we're there, we may as well add some extra flexibility and things the modeler can control about the production of figures for their model. Okay, thank you.
Thanks, Aaron. Alrighty. I was trying desperately to think of a question, but it was a little bit hard for me, I'm afraid. But David Wright has a question. He asks, are the Python scripts for these metrics in a publicly available repository?
No, they're not. They're all private, part of DeepI, I'm afraid.
Not a surprise. We've also been asked if you tried R, which may solve some of the challenges. So that's R script, am I right?
Yeah. We have tried R. The problem we have with R is it's not particularly good at developing full-fledged applications outside of dashboards. So we've just gone for consistency where most of our scripts are done in Python. We used to have a mix and we decided to go with Python over R just because it was the majority of them.
Sure. All right. What sort of RAM specs did you need to process this?
Yeah, well, it really depends on your valley. If you are running the Murray, you need hundreds of gigabytes. But if you're running a regular inland valley, you probably can get away with 64 gigabytes.
Cool. Excellent. And another couple of questions taken in. Do you have any experience maintaining both a source repository and a separate Python repository of tools? Any tips? That's also from David Wright. Maybe you two should have a cup of tea in a minute.
No. Oh, as separate repositories, yes. Yeah. There's not really anything we've done. As long as you have some sort of provenance on which version of the Python scripts produces the outputs, which is what we use Subversion for that stuff, then that's the level of provenance we've got. So hopefully you can link your source model and the provenance from the workflow together.
Sure. And our last question is from Udaya Kurata from Melbourne Water. So we've done some stuff with Melbourne Water about managing some big models. Udaya asks, aren't there standard database tools and query tools suitable for this type of work? So I guess what made you decide to use this approach?
Yeah, so if you were to use database tools and query tools, you would need to import your results every time you run it into the database. And so we figured that the time you save in the efficiency of a database versus how often we update results, it wasn't worth using that sort of approach.
Cool. Thank you. Well, you got through those tricky questions, Aaron.
Thank
well
you.
done, and thanks for that. Sounds like some pretty useful work for the, well, the stochastic modelling was very interesting yesterday, and it sounds like this is pretty important to making that happen. So well done.
Thank you.
All right, I'll let you disappear off the stage. Excellent. All right, well, we're going to take another short break. We'll be back at 4 o'clock for our last session of the day, which will be about, it was going to be a technical session on Q&A, but not many of you sent us questions. So we're going to focus on model management tools and some of the key things our developers have been working on lately. You may have seen earlier in the general chat that I posted a request. If you're calling in from another part of the world, we'd love to know where you're from. So maybe send us a message saying where you are. And if you're in Australia, then I'm more than happy to know where you are, but you just might need to be a little bit more specific than your country. So do that, and we'll be back in about 12 minutes.